Good morning, everyone. Good morning, everyone. I want to welcome you to another statistical learning class. Of course, the focus today will be on multicollinearity, and I'm also going to talk about goodness of faith. Okay, so let's get started. I think I'm going to have a recap. Okay, leading to this topic, leading to what we're doing now, we actually want to characterize relationship between variables, a response and explanatory variables. Okay, we started by way of module specification. And of course, after module specification, we actually estimated parameters in our regression model. And after the estimation of parameters in our regression model, we investigate whether assumptions hold. Okay, I remember I actually walk you through assumptions of linearity, assumptions of constant variance, assumptions of normality. Okay, and I'm also talk about whether there's an outlier or high leverage. And of course, I gave you the formula to investigate that. For high leverage, I remember I mentioned that you need to obtain what I call art matrix. And of course, with art matrix or the diagonal of art matrix, we give you the leverage of each observation. And of course, we have a threshold that you're actually going to compare each leverage, a leverage for a particular observation weight. Okay, I think I gave you 2-ish, and for small sample size, you compare with 3-ish, and of course, the h is p plus 1 divided by n. Okay, so I walk you through all of that, and I also walk you through how to detect how to see whether an outlier or leverage will be influential. Well, we did that. We achieved that by computing Cook distance. And of course, I gave you a Cook distance formula where you force estimate your parameters when a suspected observation is absent and when it is in. And of course, you compare that with a threshold of 0 0.5, whether it's greater than 0 0.5. If it is greater than 0 0.5, then there's a potential, it could be influential, and when it is greater than 1, highly influential. So we did all of that. So we are still on model. We don't just, um, yeah, we don't just make it, we don't just base our decision on empirical results from a model. We want to make sure we tidy it up. We want to make sure all assumption hold, or we want to make sure we've done what we are supposed to do. Okay. And let me also tell you this. There's one particular assumption that also need to be checked, even if you've done all of that, situation where you have so many independent variables, so many explanatory variables, there's possibility that they could be correlating. Okay, the assumption is that explanatory variables should not correlate, because when they do, it's like they are giving the same statistical information, okay, just like having two capture in a sheet, okay, and that is what we call multicollinearity. Okay, so I welcome into multicollinearity. Multicollinearity is a problem in modeling, okay, where explanatory variables actually correlate with one another. And let me tell you the reason why, at times the way we specified our model. Imagine you are building a model on BMI, body mass index. I'm going to say that again. You are building a model on body mass index, and you are now using height and weight as your explanatory variables. height and weight are expected to give the same information to body mass index. Does that make sense? Or you are actually talking about temperature and you are using temperature in Fahrenheit and temperatures in sensors in the same model. Even though you are having different data set, they're actually going to correlate. And when they do, they will be problematic to the model. Okay, so which means the method you are using, the method of estimation that we call ordinary least square, will not be able to isolate for instance, in a situation where you consider height and weight as explanatory variable to predict BMI, body mass index. The ordinary least squared approach you are using, we find it difficult to isolate effect of weight keeping height at constant. It's going to find it difficult to do that. And that's the reason why we need to investigate for multicollinearity. Now, let me tell you this. When multicollinearity is present in the, is present, okay, even, let me tell you this, your estimator, your regression estimator will still be unbiased, but they are no longer going to be consistent. And I'm going to tell you what determines consistency is variance of an estimator. Because when multicollinearity is present in a data set, it will inflate the variance of an estimator. And let me tell you this, when the variance of an estimator is inflated, the standard error of an estimator will be inflated. And don't forget the statistical inference. Okay, you need standard error if you want to construct interval estimation on your regression parameter. Okay, you need a standard error to do that. If you want to test hypothesis about your regression parameter, you need a standard error to do that. The moment your standard error is not reliable, okay, then the estimator, okay, the regression estimator will still be unbiased, but it's no longer going to have a smaller variance, which means it's no longer going to be consistent. And of course, inconsistency, if we make your interval, if you construct interval for regression parameter, we make it more wider. Don't forget, you have a wider range of the confidence interval if the standard error is large. Does that make sense? Because the standard error, the variance of estimator is inflated, the standard error is also going to be inflated. And let me also tell you this. If you conduct a t-test, that I'm still going to show you, because we use t-test to test the individual contribution of the variable, okay, explanatory variable, okay, if in a situation where practically the explanatory variable supposed to be significant, okay, your t-test will show an insignificant result. And why is it showing an insignificant result? Don't forget, if I want to conduct a t-test, I need a ratio of the estimate to the standard error. The estimate in the numerator, the standard error in the denominator. When the standard error is large, what will happen to t-value? When the standard error is large, when the denominator is large, the t-value will be small. When the t statistic is small, then the p-value associated with that will be large. When p-value is large, then it means you're actually going to reject the non-hypothesis and you're going to fail to reject the non-hypothesis and you conclude that it is not significant, even though practically it is significant. I just gave you the significance of, the consequence of multicollinearity. Okay, multicollinearity is not good. Now, I need you to pay attention to this guy. Take a look at this. That is the variance of an estimator, beta curve. Okay, now when you take a look at that, okay, if you look at the green side of that, okay, let us assume that R square equal to 0. You know, when that R square equal to 0, maybe no relationship at all. Okay, one is not explaining the other at all. What am I going to have? I'm only going to have this guy as a variance of estimator. Therefore, I'm going to say this is an inflation factor. We call this guy VIF. It's an inflated factor. If a multicollinearity is present in your data set, okay, you're actually going to have the variance of an estimator inflated. And when the variance of an estimator is inflated, the standard error of an estimator will be inflated. Don't forget, you're actually going to get the standard error of an estimator when you find the square root of the variance of an estimator. So which means what we need to do is to for of force figure out, okay, that R square for pairs of variables for us to be able to know. Now, when you take a look at what I have here, okay, this guy here is just the variation within S that you can find using that formula. Okay, and of course, sigma square, we can estimate the sigma square. Don't forget, estimation of the sigma square will be sum of square residual divided by n minus 2. Now, we need to first investigate that. Now, like I said, this is what I call the variance inflation factor, the VIF. Okay, and let me also say this. Situation where no relationship exists at all between explanatory variables, you expect that R square to be 0, right? When R square is 0, the OVIF will be very close to 1. Does that make sense? And if the OVIF equal to 1, then it means the variance of an estimator has not been tampered with. The variance of an estimator still, it has not been inflated. Okay, so that is the reason why if we want to analyze, if we want to investigate whether you know um a particular explanatory variable is problematic, is if we want to investigate if it's correlating with the other, we have a coding now. Okay, you just do VIF. And I believe my TA has already walked you through all of that. So the VIF, we got a threshold. The moment the VIF corresponding, if I have 5 explanatory variables, I'm actually going to have 5 VIF. And I will compare each of them to a threshold of 5. Okay, the VIF, the threshold, if 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 the VIF of a particular explanatory variable is greater than 5, then that particular variable is problematic. Okay, if I have 10 variables, I'm going to get VIF for each of them, and I will compare with the threshold of greater than 5. Okay, Atie has already walked you through that. So in statistical analysis, it's very, very important to, particularly in a multiple linear regression where you are looking at the effect of so many predators on the response, you need to check whether there's multicollinearity. Like I said, let me tell you this. There's possibility. The overall model could be significant, but individual parameter, individual variable may not be significant when multicollinearity exists. It doesn't make sense. How can you tell me the overall model is significant, but the individual part is not significant? The individual part is not significant because of the fact that the variance, because of the presence of multicollinearity, the variance of an estimator has been inflated. When the variance of an estimator is inflated, the standard error is also going to be inflated. When the standard error is inflated in statistical analysis, the standard error of an estimator is very, very crucial. We need standard error to test hypothesis. We need standard error to construct a confidence interval. Does that make sense? Okay. Okay, that's all about multicollinearity. I'm actually going to go into another subtopic of the day that we call inference and goodness of fit.